Okay, well, once we understand how functions of several variables can describe quantities that depend on, say, three-dimensional space, such as density or temperature, for example, there are two very natural questions that come up right away. One of them is how a function of three-dimensional space can aggregate over three-dimensional space, such as how a density can aggregate over three-dimensional space, and how that then gives us the mass of an object. And that would be the subject of multivariable integration, which is a different module. Or the other natural question is to determine how these three-dimensional quantities vary locally, because once you know how, for example, temperature varies locally, you can determine how thermal energy will flow in that setting. And that is ultimately linked to things such as the heat equation, which are governing equations for a variety of phenomena, such as the heat equation being the governing equation for heat transfer. The foundation to that is the partial derivative, and that's what we're talking about in this module, and underlying to all of it then is multivariable differentiation, which is what we're going to talk about in this sequence of talks that starts here with partial derivatives. Okay, so let's take a look at partial derivatives. And when you're differentiating a multivariable function, the underlying idea actually is pretty simple, because what you do is you substitute a vector-valued function, which is typically a straight line actually, so something very simple. You substitute that into the multivariable function, and then you compute the derivative. So if you want to look at that in two dimensions, well, here's a function of two variables, right? And if we substitute a straight line into that function, then basically what we do is we take a slice of the function, and that slice then, of course, gives us a graph that looks just like the graph of a function of one variable, like here. And that graph we can differentiate, and we can do things like compute the slope and compute the tangent line and the like. And of course, those tangent lines tell us that this quantity has a negative slope in the x direction here, positive slope in the x direction here, and so on. So that is a geometrically pretty simple idea. We will have quite a few visualizations that really rely on two-dimensional graphs, even though ultimately, as I already mentioned in the introduction, of course, we will be interested in functions that depend on three variables or even more variables, because three-dimensional space requires three variables, and ultimately for space and time we might even need a fourth variable. So other than that, well, let's just see how much we can do on a computational level, and you will see in this presentation that the computations, as long as you are okay with the derivatives of functions that involve more than one variable, as long as you're okay with holding all the other variables constant, the formal aspect is actually quite simple. It is exactly these kinds of visualizations, as well as all the interpretations that we will talk about, that make this challenging, but ultimately also insightful and useful. So, this kind of substituting a vector-valued function, like a straight line, into a multivariable function, and then computing the derivative, that in itself already is meaningful, because we may want to know how a physical quantity that is described by the multivariable function changes along the path of a particle which is described by the vector-valued function, such as, say, how temperature or pressure changes along the path of an airplane. The geometry, of course, we have seen is really pretty too, and it's a good visualization, and often we're even using these kinds of visualizations when we're talking about functions of three or more variables. But we have to be careful here, because unless you are really interested in shapes of two-dimensional sheets in three-dimensional space, the geometry really is just a visualization, nothing more. We will start with partial derivatives. And well, basically the idea for a partial derivative is that we're holding all but one variable constant, and then we analyze what happens when that variable changes, and that's of course about the simplest start possible. But all other notions of multivariable differentiation will refer back to partial derivatives, so we don't just do this because it's easy. Okay, so now let's actually look at a definition as well as the visualization in two dimensions. So we take our usual right-handed XYZ coordinate system, we look at a domain, and we look at a function that is defined on that domain? Well, if we now plug a straight line into that function, that would mean we find a point where we want to find the derivative, and then that point, of course, is also on the graph of the function. Here's the straight line now that we want to plug in that goes through that point, and we realize that that straight line, of course, which is obtained by holding y constant here, that straight line gives us a one-dimensional graph that just happens to sit in three-dimensional space, just like in the animation we just had. And in this one-dimensional graph, which we could now just rotate and sketch in a simple one-dimensional coordinate system, in that one-dimensional graph we can compute derivatives as well as compute tangent lines as usual. So the definition, which then actually applies to functions of an arbitrary number of variables, is the following. We take u to be a function of n variables, and we define the partial derivative with respect to the variable xk to be the following, at the point x1 through xn to be the following. It's called dxk of u at x1 through xn, where these are basically crooked d's. Those are not deltas. These are just d's that are supposed to be the same notation as the ddx that we had in single variable functions. They're just written differently because we want to explicitly integrate that we are taking partial derivatives, that we are taking derivatives of a multivariable function. Those things are also sometimes denoted with a subscript because this notation becomes cumbersome, and sometimes it's even denoted just with a subscript u sub k, where we're just saying, okay, we're differentiating with respect to the kth variable. And finally, what is it? Well, what is a derivative ever other than a difference quotient? How do we take derivatives? We find ourselves a base point, and that base point is x1 through xn, or here it would be the point xy. The value at that point is then, of course, f of xy, or u of x1 through xn. And then what you do is, for a derivative, you take a little step, and that little step is in the xk direction. x1 through xk minus 1 and xk plus 1 through xn are held constant. We just take a little step in the k direction. So that is exactly this kind of thing that we're essentially working along a straight line in the xk direction, which here would be the x1 or x direction. And when we do that, well, then we just subtract a value that we obtain by stepping in the positive xk direction, so stepping a little bit in the forward direction here. We subtract from that the value at the point. We can see we get a difference that is negative, and by dividing by h, we see that we get an average rate of change in that direction. And then as we let h go to 0, as we also have done in single variable functions, we get a limit, hopefully, and that is called the derivative. So the implicit assumption here certainly is that the limit exists. These difference quotients are often used in numerical computations, but when that is the case, then the quotients are actually more sophisticated than a straightforward difference quotient that we will be using here for the theory. And so that means we are not going to worry, I should have said, we're not going to worry too much about difference quotients here, because every so often, especially when things get pathological, we will certainly need difference quotients. Now, what you may find in your homework assignment or in your book is that there may be some homework problems that says use the definition of the partial derivative, that is, use difference quotients to compute the following partial derivative. Now, that will be then quite a demanding algebraic exercise. It is not something that I'm going to show here because you know how to do that algebra. It's still a good exercise, but much more important than running through those difference quotients is for us to really attach meaning to those derivatives, and that is what we will talk about throughout this presentation. Now, on the other hand, I also have to say, because we don't want to work with these difference quotients, we simply realize that for computations, the definition pretty much just means that we're holding all but one variable constant and then take the derivative with respect to that variable, right? If we go back to the definition here, if we hold all variables except for xk constant, then u is just a function of xk, and this becomes just a difference quotient function of xk plus h minus function of xk divided by h, which is exactly a difference quotient for a function of one variable, which then of course leads to a derivative of that function of one variable. And so that means When we compute the partial derivatives, computations should be very similar to what we had before. The important thing that we'll spend considerable time here will be that we also interpret the values of these partial derivatives geometrically. So, if I want to find the partial derivative in the x direction of this function f, I say partial with respect to x of x squared minus 4xy plus 2y squared, and of course now the derivative of x squared is 2x. The derivative of negative 4xy is negative 4x because the derivative of negative 4y because the derivative of x with respect to x is 1, and the derivative of 2y squared with respect to x is 0. So the one reflex that we have to get away from is just because there is a variable does not mean that that variable is our differentiation variable. And so that means because x is our differentiation variable, the derivative of x squared goes as before, 2x. Because x is our differentiation variable, we have a constant that is called 4y, not just 4. And the derivative of a constant times x is just that constant, so that would be here the negative 4y. And the 2y squared doesn't have an x at all, which means that's a constant overall, and we know the derivative of a constant with respect to x is 0. Okay, so the partial derivative in the x direction is 2x minus 4y. And that would mean then at the point 1, 0, the derivative with respect to x of that function at 1, 0 will be 2 times 1 minus 4 times 0, which is 2. That's the part that I, hopefully not perceived as a derogatory comment, that's the part that I mentioned to be quite primitive. I mean, these computations we can do, we just have to remember which variables to hold constant. And so let's work ourselves through the y derivative. Well, the derivative of x squared with respect to y is 0. The derivative of negative 4xy with respect to y will be our negative 4x. And the derivative of 2y squared with respect to y will be 4y. So this is negative 4x plus 4y just as mentioned. And if we're then interested in the derivative of f with respect to y at the point 1, 0, well, we get negative 4. What else are we going to get? So really the important part now is we also want to know what these derivatives means. By no means do I want to trivialize the computation, but you've got to be able to get into that pretty quickly, and then the main thing is we need to know what it means. So let's take a look at the numbers. The derivative in the x direction is 2, the derivative in the y direction is negative 4, and so that means if we're looking at the point 1, 0, that would mean x is equal to 1 and y is equal to 0. Let's see, how does this go? Wait. It's going this way. Let's see, no. The x-axis goes this way, the y-axis goes this way. So 1, 0 is still here. And now in the x direction, which is the direction that slants towards us, the function is going up because it's got derivative 2 in that direction, and that makes sense from this picture. In the y direction, which is this direction here, the function goes down. That also makes sense, and if you look at this picture, the perspective should also give the indication that we're going down a lot faster than we're going up. So the slope in the y direction is twice and negative that of the slope in the x direction. We can also see that in the picture. So there's a very beautiful geometric meaning that we can attach to things here. That is also something that we can read off the contour plot, even though it is a little bit more complicated to do that. Okay, so x equals 1, y equals 0 is right here. Okay, so that point is easier to find than what I did in the other plot. But now what else do we know? At 1, 0, if you look at it, plug in x equals 1, y equals 0, the value of the function is 1. So that means here we have height 1. So now in the x direction, we've got a comparatively gentle slope of 2. That means we're going up in the x direction, and we take a certain amount of space, therefore, to go from a z value of 1 to a z value of 1.2. This contour is 0.8, this contour is 1.6, that means the one in the middle is 1.2. So we take a little bit of distance to go from a height of z equals 1 to a height of z equals 1.2, whereas if we go in the y direction, we need about half that distance to go down from a height z equals 1 to a height z equals 0.8. So that's how these partial derivatives then also locally tell us how steep these functions are at the point 1, 1. Of course, if you go further, farther, you realize that the slope flattens out a little bit here, apparently also in the y direction. But what counts really is the instantaneous rate of change, the tangent lines that you have in these directions, and that's where the one in the x direction isn't nearly as steep as the one in the y direction. Okay, we move on. Yeah, this one's done. So now, as I said, the two variable examples are nice. They're beautiful in terms of geometry, but ultimately we want to look at real life phenomena, and that's where, for example, we look at space and time. So let's look at a simple space and time phenomenon, which is a vibrating string of length 1 that we want to model as follows. Each point on the string has an x-coordinate in the interval 0, 1, and a vertical displacement u from the equilibrium position, which is assumed to be u equals 0. The vertical displacement u of the point x, of the point at x, of the point on the string at x, depends on the time t, right? And that means that the displacement function for all particles on that string is u being a function u of x and t that depends on both time t and position along the string x. What I want to assume now for this example is that the displacement of the particle at position x, the vertical displacement of the particle at position x, and at time t is given by the function u of x and t being sine of pi x cosine of pi t, where x goes from 0 to 1 and t is greater or equal than 0, so our observation starts at t equals 0, as it often does in physics. And I want us to find the partial derivatives u sub t, so that's the partial derivative with respect to time, at position 1/2 and time 3/2. And I want us to find the partial derivative u sub x at position 1/2 and time 3/2, and interpret their meanings. Again, we can compute the numbers, and we will. What is important is to figure out what the numbers mean. So we continue, and well, when u of x and t is the vertical displacement of the particle at position x and at time t, then the partial derivative with respect to time is the vertical velocity of the particle at position x and time t. Basically, a derivative with respect to time is always a rate of change. That was that way when we looked at functions of one variable, and remember, the idea for partial derivatives is you hold all variables except for one variable, in this case the time variable, constant, and so that means you're still talking about a derivative with respect to time. What is the function that you're differentiating? The function that you're differentiating is a vertical position function, namely this u here. There we go. Okay, that's the u. It's a vertical position function. Of course, when you take a position function and differentiate it with respect to time, you always get a velocity. And if that's a vertical position function, well, then you just get a straight vertical or up-down velocity at that position and at time t. If we're looking at the derivative with respect to x, well, okay, so now we hold time constant, which means, as we have also seen in the presentation on functions of several variables, we're taking a snapshot. That snapshot now is something where x is a space variable, and we just look at something that is modeled with a function. And so basically the string now is just a function of space of an input variable x, so it's just a y versus x or z versus x graph, and in such a graph the derivative is a slope, and so the geometric meaning there is the slope again. We will see that also in an animation, but now let's also compute the functions, the derivative functions. So derivative with respect to time of u at x and t is d dt, or partial with respect to t of sine pi x cosine pi t. Well, sine pi x is of course constant, so that stays with us. Constant with respect to t, that stays with us, and so the derivative is just determined by the derivative of the cosine function. So you get negative constant sine pi x times negative sine pi t, which is the negative and the sine pi t, and then from the chain rule you still have to differentiate the inside, which is pi t, and the derivative of that with respect to time is of course this pi here. Okay, the derivative with respect to time at x equals 1/2 and time t equals 3/2 now is just that you plug in x equals 1/2 giving you sine of pi halves, and t equals 3/2 giving you sine of 3 pi halves. Well, sine of pi halves is 1, sine of 3 pi halves is -1, and so that means your derivative with respect to time at that point in space and time is pi. We're looking at the x derivative. Well, that's partial with respect to x of sine pi x cosine pi t. So this time we get cosine pi x times pi from the derivative of the first term with respect to x, and we get the pi from the derivative of the inside using the chain rule. And the cosine pi t does not depend on x, and so therefore that's a constant, which we just copy down. Okay, well then we want to also find the partial with respect to x at 1/2 and 3/2. And that means we just plug in x equals 1/2, t equals 3/2. We get pi times cosine pi halves, cosine 3 pi halves. We actually could stop right there, because cosine pi halves is 0, and so 0 times anything is 0. So the derivative in the x direction is 0. Let's take a look at what that looks like. Remember, the time derivative at this point was pi. The space derivative was 0. And if we are looking at this oscillation, well, let's remind ourselves of how we visualize this. On the left, we actually see the animation of the vibration of this string in time. All the time snapshots are sine waves, sine half waves, if you will, and those things just go up and down. So that is the whole the whole string as it vibrates. The blue point here is the point at x equals 0.5, and we can see that this shape here remains a sine wave, and the blue point stays in the middle. And that means if you're in the middle of one of those half waves, technically, of a sine function, then of course you are at a maximum and the slope has to be 0. And so the derivative of this function that models the shape of this vibrating string, the derivative with respect to x at x equals 1/2, will be equal to 0, not just at time 3/2, but actually at all times. Okay, so that is our attention to this. Now let's take a look at what happens when we really just look at how the particle at x equals 0.5 travels. That particle, of course, travels down, and up in this animation. That just goes from 0 to 4. And so that means, let's just run it all the way through and then stop it. About here, yeah. Well, then we need to look at what the time derivative, which would be the derivative of this graph here, because now we're plotting position over time. We would want to know what the time derivative is at time equals 3/2, and at time t equals 3/2 we get a positive slope. And once you really work out exactly what that is, that slope turns out to be a little bit more than 3, namely it turns out to be pi. So that is the interpretation, and again, like I said, the computations we can do pretty quickly. We need to know what it means. Of course, when we get to 3 space variables, things get more complicated, because all of a sudden we can't draw the graphs anymore. We can do things like sketch, goodness, what are they called? The level surfaces, which then, for example, for a function that assigns equal values at equal distances from a certain center point, like we have here, then we've got these these level surfaces that are basically concentric spheres. And if you then take a derivative, say, in the x direction, then basically you determine how fast, if the colors actually encode size, which they often do, then you differentiate, then you compute the instantaneous rate of change, or the local rate of change of those colors in the x direction, which may not have terribly much meaning until we connect that to something that can be interpreted, such as in this NASA image that I'm very happy that NASA makes available under their fair use policy, which is that if you have an image like this cutout of the sun here, where the various colors tell you how hot the layers of the sun are, then if you're interested in the rate of change of the temperature in this area, for example, in the direction of, let's assume that this is the x-axis here, so the coordinate system has been rotated a little bit, well, then you know how fast heat drops off or increases, probably drops off in this direction. And that then in itself will also tell you a bit about convective currents and about how heat transfers inside the sun. All right, so in terms of that, then the computations themselves we might as well just look at something that has more variables to really just get used to the whole thing. If we want to find the partial derivative, partial with respect to xk of the function 1 over square root x1 squared plus x2 squared plus and so on plus xn squared. So that is 1 over the n-dimensional distance from the origin. So it's just a more general relative of the function that we have just seen in the three variable cutouts, as well as in the picture of the sun. If we're assuming that the heat was really dropping off like that, it probably had a different shape, but the profile itself is the same. The level surfaces for this function are all concentric spheres. Okay, so if we take a partial derivative of that, well, we just decode it. We realize that this is the derivative with respect to xk of something raised to the negative 1/2, right? Because when you take a square root, that means you raise it to 1/2, and if you divide by it, that's just a negative exponent. So this is now a little bit easier to read for a power rule. And now I just take the derivative with respect to xk using the regular chain rule, because remember, partial derivatives means you hold everything but xk constant. So that means I have the derivative of that outer function, which is negative 1/2, times whatever is inside raised to the negative 3/2, because that's just going with the power rule. I apologize. And then you take the derivative with respect to xk of the inside, and that is 2xk. And that then simplifies to negative xk, because the 2's cancel, the xk is a numerator. And this can be encoded again a little bit prettier. It can be encoded as square root of x1 squared through plus x2 squared plus and so on plus xn squared cubed. So that means that the derivative of 1 over the distance from the origin, the partial derivative with respect to xk, is actually negative xk divided by the distance from the origin cubed. So what does that tell us? Well, the derivative is negative. That certainly makes sense because this function gets smaller as we get away from the origin, and it drops off at a pretty steep clip here because the slope now is actually proportional to the cube of the distance, or is ultimately not sloped very much anymore, because if you've got a distance from the origin that is bigger than 1, then you're dividing by a distance cubed, and that becomes something that flattens out pretty good. That also makes sense because 1 over r is a function that flattens out pretty good if you draw r versus 1 over r, for example. Okay, so of course you can also take higher order derivatives, and the best way to introduce those or to motivate those is that we look again at acceleration and concavity of that vibrating string. If we go back to this animation and ask what about the acceleration and the concavity, well, the concavity of course tells us how much that string bends, and that's where we can see throughout the rotation. Well, at first the string of course bends quite a bit. Then if you go through 0, and of course here, that's where the string is not bent at all. That's where the string is right straight. And then of course ultimately the string is actually concave up versus having been concave down at first. So we should be able to have something that tells us a bit more about these geometric quantities. And at the same time, of course, if we go around, then even though the velocity at these minima and maxima is 0, that's where, because you have to turn around, that's where the acceleration is highest for the particle, whereas once you go through the origin, here, when you go through the origin, the function position versus time looks sort of like a straight line, and the second derivative of a straight line is 0, which means the acceleration around here actually will be 0, and we'd need a way to compute that. And of course we have that way because we know that the second time derivative of the position, or the time derivative of the velocity, that's got to be the acceleration. And we know that the second space derivative of a slope has got to be the curvature, the concavity. And so that's what we can define very easily. Again, we're looking at this as a function of n variables, so we don't have to worry about 2 variables, 3 variables, more variables, variables that are space and time, and so on. Look, it's a function of n variables, and the interpretation depends on the context of the function. So you take one of those functions, and we can define the second partial derivative with respect to xk and xj at the point x1 through xn to be d2 dxj dxk of u at x1 through xn, which is also sometimes written u xj xk of at x1 through xn, or simply u sub jk x1 through xn, and that is simply the partial derivative with respect to xj of the partial derivative with respect to xk of the function, provided that that partial derivative exists. Okay, so before we get back to this vibrating string, let's actually take a look at a geometric example here. Let's look one more time at our function f of xy equals x squared minus 4xy plus 2y squared. We want to find all second partial derivatives at the point x equals 1, 0, where we previously have analyzed that function. And then we want to interpret their values geometrically. All right, well, the second derivative of f with respect to x, that'll be the derivative with respect to x of the x partial derivative. The x partial derivative is 2x minus 4y plus 0, so we need to take the derivative, the partial with respect to x of 2x minus 4y, and that ends up being 2. The second partial derivative with respect to y will be, well, partial with respect to y of partial f with respect to y. Partial f with respect to y will be 0 minus 4x plus 4y, so we get partial with respect to y of negative 4x plus 4y, which with respect to y has a partial derivative of 4. When we take the second partial of f with respect to x and y, well, that's the derivative with respect to x of the partial with respect to y of xy, or the partial with respect to y of xy was this negative 4x plus 4y here, so we get that again. We get partial with respect to x of negative 4x plus 4y, and we get negative 4. And of course we could also take the second partial of f with respect to y and x, which technically is something else, right? It's the partial with respect to y of the partial with respect to x of f, and so that would mean we take the partial with respect to y of 2x minus 4y, and that turns out to be negative 4 also. And it turns out that this equality is not an accident. That is ultimately the idea behind the subject of Clairaut's theorem, which we'll talk about in just a little bit. If we want to look at that, well, second partial derivatives, if we're looking at what we have here, then the second partial derivative in the x direction tells us a little bit about concavity in the x direction. And it looks like the function is concave up in the x direction, and so I hope that that will actually work out. Let's see how that will go. Yeah, x equals 1, y equals 0. It should be concave up. And that's correct because we have that the second partial in the x direction is 2. If we're looking at the change in the y direction, it also looks concave up in the y direction, and that is also consistent with what we have here. We have a positive second partial in the y direction, and this all comes straight from the geometry that as long as you keep taking partial derivatives in only one space direction, basically what you're doing is you're taking derivatives of that slice that you have taken in that space direction, and so those partial derivatives are exactly the same as what they would be for a function of one variable, or they have exactly the same meaning for good reason. You're holding everything but one variable constant, and so essentially you have a function of one variable that just depends on a couple of fancy constants. The interesting thing is, of course, the mixed partial derivatives, and for those actually I've got some animations because those mixed partial derivatives are really hard to interpret. So basically, if we are looking at the partial derivative of the x partial derivative in the y direction, then basically we're going along the y-axis. And along the y-axis, we're trying to figure out how fast the slope in the x direction is changing, right? So partial with respect to y of partial with respect to x is partial with respect to x tells us the slopes in the x direction, and the partial with respect to y of that thing tells us how fast the slope in the x direction changes. So in this animation, I have blotted things out in such a way that I just have straight lines in the x direction, and those are the straight lines along the line y equals 0, and so that gives us exactly the slopes at those various points from 0, 0 through 1, 0 to 2, 0, and so on. And that's exactly the wrong way around. Okay, we're going along. Yeah, we're going along the y-axis. All right, let's make sure of that one more time. This is the slope in the x direction, so we do that at x equals 1, I think, and so we get the slopes at 1, -1, 1, 0, 1, 1, and so on as we're moving in the y direction. And we're seeing that change here. And so basically the mixed partial derivative df dy dx tells us exactly how fast this twists, and that's what the caption here also said. It tells us how warped the surface is. We can also take a look at that if we are looking down the y-axis. That's where it becomes a bit better to see how this tilts, right? The small y coordinates are in the back, the large y coordinates are in the front, and I'm looking down the y-axis, and the way I've rotated it is that the x-axis actually points towards the left, so that means we're going from positive slopes to negative slopes, and that means we've got a negative warp, which is exactly what this animation describes here. All right, so that was that. Clairaut's theorem says that equal mixed partial derivatives are not an accident. I already mentioned that, and so the theorem, which is Clairaut's theorem, says that if you've got a function f of n variables that is defined on an n-dimensional ball B around the point a1 through an, and if all second partial derivatives of that function exist on that ball and are continuous at that point, so we need some technical hypotheses here, but if that is the case, then for all indices I and k, we have that the second partial derivative of f with respect to xi and xk is the same as the second partial derivative of f with respect to xk and xi. So it doesn't matter in which order mixed partial derivatives are taken, as long as certain technical hypotheses are satisfied, which it turns out usually are satisfied in practice, pathology, as we're going to examine, notwithstanding. Okay, the proof is deferred to a later presentation. We don't have the machinery for that right now, but we can already understand that under certain technical hypotheses, things will work out nicely, and so that is a good theorem, right? It says certain things are actually easier than we could have anticipated in a worst-case scenario. Okay, moving on. We can then, because the order in which higher order partial derivatives are taken does not matter, we can induce a couple of notations. So an mth order partial derivatives with respect to xk1 through xkm, which is also written as u sub xk1 through xkm, which is also written as u sub k1 through km, if you just want to write the indices. That stands for the mth partial derivative, where the derivatives are taken in the order in which they occur from right to left in the denominator. So first you differentiate with respect to km, then with respect to km minus 1, and so on, and so on. And that's whether it's the denominator or the subscript, right? And because under hypotheses that are very similar to Clairaut's theorem, basically the mth order partial derivatives all have to exist and be continuous, then under these hypotheses, higher partial derivatives can be taken in any order, and that means if we've got, say, m1 through mn that add up to m, we then often write that the mth partial derivative with respect to x1 to m1 through all the way to xn to mn of u of x1 through xn is that you take the mnth partial derivative of u with respect to xn, then you take the mn minus first partial derivative with respect to xn minus 1, and so on all the way to taking the m first partial derivative with respect to x1 all the way at the end. That is something that allows us to sort things out a little bit, so we don't have to worry if we take a really higher order partial derivative in which order the partial derivatives are taken, and so we just aggregate. If we take 5 x1 derivatives and say 10 mn derivatives, then they're all just aggregated in these symbols. And the good news here also is that we won't need these higher order derivatives very often, because most of the governing equations for physical phenomena only involve up to second derivatives. If we go back to the string, well then when u of x and t is the vertical displacement of the particle at position x at time t, well then the second derivative with respect to time, well that is the second derivative of the vertical position with respect to time. the second derivative of a position is an acceleration. So this is the vertical acceleration of the particle at position x and time t. And the second derivative with respect to x, well, remember that when we hold everything except x constant, then that string really is just a one-dimensional graph, and the second derivative in the space direction of a one-dimensional graph is concavity, and so uxx measures the concavity of the string at the position x at time t. Now u of xt measures how the slope at that point in time changes over time, and that is something that we can also record, but very often actually we will typically just have derivatives that use time or space all the way. That is also something that happens at least in the governing equations in their simplest form more often than not. That doesn't mean you won't have mixed partial derivatives there, but that's when things get a little bit hairier. All right, so let's finish out with some words on pathological examples. First of all, as I already mentioned, unless you're a math major, it is unlikely you will deal with these pathologies very much. And even if you're a math major, unless you're really looking at something very nasty, you often also don't have to deal with those pathologies. So practitioners mostly work with partial derivatives, and there are reasonable conditions that exclude the pathologies, such as the hypotheses that we have for Clairaut's theorem, which we will revisit in various guises as we go through this module with presentations on partial derivatives or on multivariable differentiation. At the same time, understanding the pathological examples will improve our visualization skills, and that means we might as well do it, and it will also improve our understanding ultimately of why the definition of differentiability for multivariable functions is as complicated as it is. It's a very simple reason: there is no choice. Well, okay, that's the simple upshot, but all these pathologies will lead up to that. So as an example, let's take the function f of xy equals xy over x squared plus y squared as long as we're not at the origin. And let's make it 0 at the origin. We want to find the partial derivatives at the origin and interpret their meaning. Well, the partial derivative with respect to x at the origin, this is a piecewise defined function, so we really have no choice but to compute the difference quotient. And what do we have? A partial derivative in the x direction means we take a little step. We have a base point, and that base point is the origin. We take a little step of length h in the x direction, so we go from the origin 0, 0 to the point h, 0, and we divide by the step length, which is h. And look here, if you evaluate the function at those 2 points, you get 0 minus 0 over h, so the fact that h goes to 0 doesn't matter at all. You get that your partial derivative is 0. If you do the same thing in the y direction, well, same story. Your base point is 0, 0. You take a little step in the y direction of length h. You subtract these two values from each other and divide by the step length. And whoop, there was a hidden link. Let me cancel that real quick. Cancel that one too. We'll see the link in just a second anyway. And so now these values here are, of course, 0 minus 0. So again, we get the same limit, 0 minus 0 divided by h. We get 0. And so that means the slope in the x direction as well as in the y direction is equal to 0. But there is a problem because the function isn't even continuous. And so this here was that link that I accidentally activated just a second ago. We'll take a look at the picture in just a minute, or in just a second. But what do we remember from single variable functions? Single variable functions had something that said, if the derivative exists, then the function is continuous. Well, here we have a very natural notion of derivative, namely partial derivatives. And these partial derivatives exist in a very nice way for this function, but the function isn't even continuous. And of course, once we look at the picture, which is actually in this MathCAD sheet, we can see what's going on. If you go in the x direction, you're going pretty much along a horizontal line. If you go in the y direction, you go along a horizontal line, and that line is at height 0. And that means in those directions, as long as you don't see the other direction, it looks like everything is flat. But of course, as soon as you see the other direction, you see that there is a big discontinuity, and so that differentiability at this function isn't necessarily something that or this idea of differentiability isn't necessarily something that we would want to associate with this graph in particular, because we would ultimately want to have a notion of differentiability that goes in the direction of being able to fit this thing smoothly to a plane, which we can't do because it isn't even continuous. And so if we want to be able to fit something smoothly to a plane, it at least has to be continuous. And so that is the kind of thing that we will have to struggle with a little bit. Now, the first thing that we can see here, of course, is at least for this example, the pathology is no longer a pathology if we look in all directions, if we don't just try to take derivatives in the x and the y direction, but also along directions that are sloped away from the origin. And that is indeed the subject of talking about directional derivatives, and we will have a separate presentation on that. Before we get to the directional derivatives, we need to take care of some technical aspects, and that is the next presentation of the multivariable chain rule. That is the one aspect that gets a little nasty because we have to keep track of a bunch of variables, but as soon as we have encoded that chain rule, and there are various ways to do that, the computations actually aren't that bad. So for now, well, you've got homework to do. There'll probably be some computations, hopefully the derivatives. You just need to get used to making sure you know which variable, with respect to which variable you're differentiating. If you've got a couple of difference quotients on there, then your teacher, including myself, probably had a good reason to put those on there, so don't disrespect those, do them also. If there is some stuff about pathology, well, that's where the air gets a little thin. But overall then, the main thing certainly is whatever problems you have that have an application, try to interpret what the derivative actually means. What kind of slope of what are you actually computing? What kind of rate of change are you discussing in the various problems? Because that is exactly what ultimately will give you your understanding of the physics, of the engineering, of the science, of the more advanced mathematics that will come after you're done with the calculus sequence. All right, I'll see you for the multivariable chain rule.